More recently, using satellite observations, European scientists have created this chart. So this is the leakage rate in percentage. This is the range that we predicted, 3.6 to 7.9. Here's what EPA is still estimating today. And these are the various measurements made. And as you can see, the measurements that are made are largely outside, above our original estimates. And if we then go back and recompute what we did in our paper 4 years ago and compare coal to oil to conventional gas to shale gas using the as measured, not the estimated, but the as measured methane emissions, we now get this chart. The black line is the error bar. Could be this low, could be that high. Here's the mean. This is expressed in equivalent amounts of carbon dioxide. How do you get from methane to carbon dioxide? You get there by something called a global warming potential, which is the next thing I'm going to explain when I answer the second question. So the technology question is now largely answered. There's more methane being emitted than we thought. A lot more than the EPA is estimating. Next question. Now that we know how much is being emitted, what impact is it having on climate? Answer, hell of a lot. How do we know that? Because you can compare the relative warming effects of any greenhouse gases. If you say, let's use carbon dioxide as a standard, the global warming potential, how much warming will occur if I put 1 kilogram of carbon dioxide in the atmosphere, call that 1. Now we take another greenhouse gas like methane, and using some sophisticated atmospheric chemistry, we calculate how much warming will occur if you put a kilogram of methane in the atmosphere. The ratio of those two is a global warming potential, GWP. So that global warming potential depends on how much you understand atmospheric chemistry, which is an extremely complex science. I don't understand it. And over what period of time you're going to make that comparison. Do you want to compare them instantaneously? Here goes a kilogram of carbon dioxide, here goes a kilogram of methane. What's the comparison? Or do you want to wait 20 years and see the cumulative effect? Or 100 years and see the cumulative effect? So both of those factors are included in this chart. IPCC stands for Intergovernmental Panel on Climate Change. That's the organization consisting of scientists and engineers from around the world who are doing their very best to study climate change. They issue reports roughly every 7 or 8 years. In 1996, they said that methane is, in a 20-year period, 56 times more potent than carbon dioxide as a global warming agent. If you want to wait 100 years, it's 21 times. So methane is important. Fast forward to 2007, they increased the 20-year factor from 56 to 72, the 100-year factor from 21 to 25, and that number 25 is in red. I'll tell you why in a minute. But back in roughly 1997, the U.S. Congress modified the Code of Federal Regulations, the Federal Code of Federal Regulations, to entomb that number 21. By federal law, the United States government declares that the global warming potential of methane is 21. It's the law of the land. Hasn't been changed. Fast forward to 2 years ago, the last report from IPCC says, no, we were wrong, it's not 56, it's not 72, it's 86, it's not 21, it's not 25, it's 34. And I threw in another paper in here just for the interest of it. So by law, the United States government says the global warming potential is 21, and we have to use the 100-year period to make the judgment. Current science says, well, if you're going to use the 100-year period, it's not 21, it's 34. 34 is more than 50% higher than 21. But why are you using the 100-year period? Is that because you have to? Is there a rule that says, or is there some science that says you have to use the 100-year period? We'll talk about that. How much is too much? How much methane emission is too much? Well, it depends upon what you're worried about. If you want to convert all of the automobiles in the United States from using gasoline to using natural gas, in order for there to be a climate benefit, the leak rate would have to be less than 1.4%. What is the current leak rate? Somewhere around 5, maybe higher. So it doesn't make any sense to convert all cars to natural gas. It makes even less sense to convert heavy-duty trucks from diesel to natural gas. The leak rate would then have to be less than 0.8%. But how about if we converted all our coal-fired power plants to natural gas? Isn't that good? We can do away with coal. That's good. But if we do away with coal for electricity generation and substitute natural gas, the leak rate would have to be less than 2.7% to have a climate benefit. How much is enough? In order for there to be a benefit, in order for natural gas to be a bridge fuel, the leak rate nationally has to be less than about 2.7%, and the data I just showed you says no way. Which leads us to energy policy. Now we know how much is leaking. We know what the impact on climate is. We know what the break-even point for electricity generation is. What should we do? I'm speaking as President Obama, the EPA, and the US Congress. Wow, what an awesome responsibility that would be. We make policy. We issue reports like the EPA's Clean Power Plan. It's a proposal issued by the EPA earlier this year that says each state has to make a decision on how to transition from where we are to where we want to be to fight climate change. And the federal government declares that natural gas is clean. It can be an intrinsic large part of any state's portfolio. The federal government encourages it. That's a policy decision. Okay. Should that policy decision be based on a 20-year time horizon or a 100-year time horizon? That's a policy decision. This is from the IPCC latest report. It says that whether you choose 1 year, 18 years, 26 years, 87 years, that's policy. Depends upon what you're worried about most. Are you worried about the economics, or are you worried about climate change? There's conflict there, isn't it? So, the present administration's Clean Power Plan declares that natural gas is clean power, and it uses a global warming potential of 25 on a 100-year basis. I know I'm going fast here, so let me back up a couple slides here and make sure you understand. The current science says that if you're worried over the next 20 years of climate change, you should be using 86. If you want to forget the next 20 years and say, we hope that 100 years from now we'll still all be around and climate will not have pretty much changed the way we live on Earth, then we should be using a factor of 34. The federal government, in its current proposal, uses a factor from 2007, and it makes a policy decision that you and I, as citizens of the U.S., are going to look beyond 20 years of climate change and worry about not our children, not our grandchildren, but our great-grandchildren. If we ever get that far. All right, last two slides. I'm going to compare the implications of what I just said in the Clean Power Plan, the proposed Clean Power Plan. It's not yet regulation, it's not a rule, it's a proposal. This is science. I'm going to show you a science chart, and I'm going to show you a government prediction. This is year. So here's 2000, here's where we are, 2015. This black squiggly line is actual measurements of global warming. So this is global warming in degrees centigrade. Here's the fateful 2 degrees centigrade that most scientists say we should never get close to. If we get to 2 degrees centigrade global warming on an average Earth scale, bad things most assuredly will happen. Worse things than we've seen today. Each of these 4 lines is the result of multiple computer simulations, a prognostication, a prediction of the future based on knowledge of the past and our best available scientific insight into the causes of climate change. These are not facts. These are simulations. They're predictions. 4 different scenarios. Scenario number 1, called the reference case. Paris fails. In December of this year, there will be again a climate summit in Paris. Paris fails. We can't come to an agreement worldwide to decrease our use of fossil fuels. We keep using them at the same increasing rate that we're currently using them worldwide. The computer models say we get to 2 degrees centigrade in 2042. 17 years from now. Should we be worrying about 100 years from now or 20 years from now? If we had started in 2010, when this chart was created, drastically reducing CO2 emissions, we delay getting to 2 degrees centigrade to roughly 2045. Doesn't do much good. Because carbon dioxide, it's in the atmosphere now, began to come out at the beginning of the Industrial Revolution, and stays in the atmosphere for over 1,000 years. Unless you can suck it out of the atmosphere, it's there. So you can stop putting carbon dioxide in the atmosphere today. We could stop burning all fossil fuels today. Yeah, right. It wouldn't make a damn bit of difference. We're going to get to 2 degrees centigrade. On the other hand, if you decided you were going to substantially decrease methane emissions and soot, BC is black carbon, soot, which you see coming out of diesel, and when you burn impure stuff coming out of a gas well on a flare, and you see the black stuff coming off the flare, that's soot. That has an almost immediate effect. It delays our getting into 2 degrees centigrade up to the year 2070, buys some time, but it doesn't solve the problem. What we were supposed to be doing, starting many years ago, back here, was drastically reducing our use of fossil fuels, which would have resulted in a decrease of CO2 emissions, a decrease of methane emissions, and a decrease of soot. And the computer models say, we luck out. We get to over 1.5, but we don't get to 2 by mid-century. Things are still going to be different and difficult by then. There will be continued sea level rise. There will be more extreme weather events. There will have to be some migrations of significant populations in certain places. But maybe we avoid catastrophe. That's the science. This is the prediction of our federal government. From the U.S. Energy Information Agency, which is part of the U.S. Department of Energy, this is retrospective. This is the latest data pulled down this morning. This is a look backwards from 2013 to 1980 of what kind of fuels are used in the U.S. for energy generation. Transportation, home heating, hot water, electricity. 2013, 27% of our energy was coming from natural gas, 8% from renewables, 8% from nuclear, 18% from coal, 36% from oil. The prognosis of the federal government is in 2040, here's 2040, if we don't do anything significantly different, from what we're doing today, the computer models say in 2040 we're going to be right here. 2 years from, here's what they predict. Not significantly different than we're doing today. The current estimate of the Department of Energy of the United States says by 2040 the United States will be getting 10% of its energy from renewables. Where the hell's the bridge? Excuse me, where's the bridge?
Nowhere.
Thank you. So there you have it. I promised 2 more slides, but there's 2 more. I told you at the beginning I was going to come back to that database I showed you that we have online for you to look at. And I pointed out that those 620 papers or whatever it is, this is a graph that shows how many of those papers were printed, peer-reviewed. This is not junk science. This is not blog science. This is peer-reviewed publications. 2009, 6 papers. 2010, 6 more. 2014, there were 192 papers. As of June 1st of this year, there were already 103 papers. So 50% of all we know in the peer-reviewed literature about the impacts, some of which I talked to you about tonight, not all of them, 50% of what we now know in the peer-reviewed literature we learned in the last 18 months. In other words, there were large-scale experiments going on in a technological gamble before we knew what the consequences might be. It's not too late. But here's what the science is saying as of now. If we analyze those 620 papers, which we divided